Hello, this is Dr. Krause with an introduction to frequency response of dynamic systems. This video serves two purposes. One, hopefully it will be generally useful to anybody who comes across this on the internet looking to better understand frequency response and Bode plots. But also specifically, I want to give my students an example before we vote tomorrow of what it looks like for me to give a technical lecture using my document camera. So if you find this to be helpful or annoying, let that feed into our poll on whether or not to continue lecture flipping. So a couple of big ideas. Frequency response is a very powerful tool for system identification. It can be more powerful than time domain responses such as step responses or impulses. We are going to assume a steady state. Steady state doesn't really make. I'm going to have some issues with the word steady state. We'll come back to that. But I'm assuming a fixed sine input, at least in the analysis. We are trying to find why steady state will be the response after transients die out. We'll talk about what that means in a second. So the term steady state is a little bit confusing or misleading potentially in that it's really not, it's still going to be time varying because it's a sinusoidal input. So we're going to have a sinusoidal output. But it is after any transient terms die out. So it's I don't know what else to call it. So I call it Y steady state kind of out of habit, but it is not going to be constant, and that might be frustrating to some people. So basically what we're saying is we've got some system with some input U, some plant transfer function, and some output Y. And part of what we're getting at is that if U of t is some sine omega t term, then I can find my steady state y to be some magnitude sine omega t plus some phase phi. And I can find this, and we know this is a transfer function, so g sub p of s is equal to y of s over u of s. And specifically, if this is our u of t, then we know that u of s is omega over s squared plus omega squared. So I could find y of s as g sub p of s times omega over s squared plus omega squared, and then I could do partial fraction expansion and find the exact solution for y of t. But this is a little bit time consuming, a little bit algebraically intensive, and unnecessary. My claim is that we want to learn how to do this, and it will be very, very powerful and very, very useful. And it will turn out that the magnitude m is just the absolute value of g evaluated at s is equal to j omega, and that phi will turn out to be the phase of g evaluated at s is equal to j omega. And so occasionally I'm going to write g j omega, and that's going to be understood to mean g evaluated at s is equal to j omega. So that's a little bit of my shorthand. And so my claim is if we can learn, so this is a whole lot faster than doing the partial fraction expansion. We can also do this for a range of omegas or create a vector of omegas or an array in Python terms and plot these, and that will turn into a Bode plot. And a Bode plot will be a super useful tool for understanding the dynamics of a transfer function. Also, a Bode plot is super easy to generate experimentally, especially if we have a swept sine input where omega is a function of t. And I can find g j omega experimentally by simply taking the FFT of my output signal, divided by the FFT of my input signal. And so by choosing my input signal carefully, measuring my output signal, I can generate a swept sine over a certain frequency range. This is super easy to generate experimentally. Once I have the data, generating the Bode plot is really, really easy. And then it becomes really, really apparent where the poles and zeros, for example, of my transfer function are. And so it does a whole lot more to tell me about the form of G sub p than simply a step response or an impulse response can. So I want to prove in the next little bit here that this is true and show how we calculate them, and we'll go from there. So first thing I want to show is why it's true that YSS can be written as magnitude times sine omega t plus phi, where m is equal to the absolute value of g j omega, and phi is equal to the angle of g j omega. So let's jump into that. Let's start off with a first order system. So let's assume that g sub p is equal to p over s plus p. And as I said, that is y of s divided by u of s. And we're saying that u of s is omega over s squared plus omega squared. So y of s would be g sub p times u. So y of s will turn out to be p over s plus p as a quantity times omega over s squared plus omega squared. Now, if I was going to set up the partial fraction expansion of that, I've got a pure sinusoidal input, and so I would assume the possibility of both a sine and cosine output. So knowing what's in my Laplace transform table, A omega over s squared plus omega squared is a sine term, and B s over s squared plus omega squared is a cosine term. I would also potentially have a term related to the pole from my transfer function. So if I was doing a full-on partial fraction expansion, this would be the way to go. I could then multiply through by this entire denominator. Keep in mind, this is our g sub p for this first order example, and this is u of s. But one of the things I want to show is that we're always going to have these kind of terms in addition to our sine and cosine terms that come from the poles of our transfer function. And as long as, so this only works if we have a stable transfer function. This analysis absolutely breaks down and is totally not valid if the transfer function isn't stable. And that will be an issue for our project later. But assuming that we have some transfer function system, I want to multiply through by s squared plus omega squared on both sides of this equation. So this is going to cancel here, and this is going to cancel here. And what we're left with would be p over s plus p times omega is equal to a omega plus bs plus s squared plus omega squared as a quantity times c over s plus p. And again, this is g sub p. And I'm going to argue that as long as the transfer function is stable, when it comes to, if I'm only interested in the steady state response of y, I don't care about whatever these terms are. So I'm going to take on both sides of this equation and plug in s is equal to j omega. So in this particular example, with the first order transfer function plugged in, I would get p over j omega plus p times omega is equal to a omega plus b j omega. And then this becomes j omega squared plus omega squared c over s plus p. And the key thing to see in this, well, it's a couple of things. So this I would call g j omega. It's the transfer function evaluated at s is equal to j omega. And I've plugged in a j omega for an s here, and I've plugged in a j omega for an s here. And then the other key things to see is what happens when I take s squared and substitute in a j omega for s. Well, I get a j squared omega squared. Well, j squared is a -1. So I get a negative omega squared plus omega squared. And this is the key to this whole technique of finding the steady state response faster without having to do a full partial fraction expansion, is that this term goes to 0. So in a simplified version of this thing, I'm left with p over j omega plus p times omega is equal to a omega plus b j omega plus 0 times my c over s plus p. Now, it wouldn't matter how many terms were here. They would all be coming from the poles of the transfer function, and there could be many, but they're all multiplied by 0, so they're all going away. So when it comes to finding the steady state response of a stable transfer function to a sinusoidal input, we're left with p over j omega plus p times omega is equal to a omega plus b j omega. And at that point, I can divide an omega out of both sides. And so a is equal to the real part of p over j omega plus p. And b is just equal to the imaginary part of p over j omega plus p. But if we wanted to write this as a more general notation, we could say this is the real part of g j omega, and this is the imaginary part of g j omega. So we could do other quick examples. I mean, for example, if I had a second order transfer function, so if g sub p was equal to omega squared over s squared plus 2 zeta omega n s plus omega n squared, and I still had u of s was equal to omega over s squared plus omega squared, then it would still turn out that y of s would equal g sub p times u. And so I could again set up a partial fraction expansion. And if I were trying to find the full solution to this, this would be a little bit complicated. So I would now have I would write it as a c omega d. Yeah, because I got multiple different omegas here. That makes things a little bit complicated. Plus a d s plus a over s plus a quantity squared plus omega d squared. And if that looks a little bit odd to you, this has to do with completing the square on this term and the definition of omega d, blah, 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 blah. In the end, I don't care if I'm only trying to find the steady state sinusoidal response, because I'm going to take both sides of this equation and multiply it through by s squared plus omega squared. And so as before, I'm going to get, and again, this is g sub p. This s squared plus omega squared will cancel that s squared plus omega squared. And so I will get omega squared. Well, this should be omega n squared. Sorry, that's confusing. I got too many omegas going on. Omega n squared, s squared plus 2 zeta omega n s plus omega n squared as a quantity times omega is equal to a omega plus b s plus, and then again I'll have this s squared plus omega squared term from my sinusoidal input that will multiply my c omega d plus ds plus a divided by s plus a quantity squared plus omega d squared, blah, 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 blah. But when I plug in on both sides of the equation, s is equal to j omega, this term will again go to 0. So again, I don't care what's in these brackets. It's all going to get multiplied by 0. And this will always just be G sub P evaluated at S is equal to J omega. So if I wanted to generalize this for any stable transfer functions, I for now don't have to know what G sub P is. But if Y of S is G sub P U of S, and if U is a sinusoidal input, then Y of S will just be G sub P of S times omega over S squared plus omega squared. And if I was trying to do this as some kind of generalized, I don't necessarily care what's going on in G sub P right now, then I could write it in this form. I'll have my sine wave or sinusoidal and cosine, sine and cosine terms, and then I would just have some other stuff. And that other stuff would all depend on the poles of G sub P. But when I multiply both sides of the equation through by S squared plus omega squared, and then evaluate at S is equal to J omega, I get G sub P evaluated at J omega. This one cancels and that one cancels when I multiply through. So it's times an omega is equal to A omega plus B J omega plus 0 multiplying these other things. So that's why I don't really care what's in here. It's multiplied by 0. And so in general, I'm left with my transfer function evaluated at J omega, and I can divide an omega out of both sides of this, and so that will equal A plus B J. So it turns out that A will always just be the real part of G sub P evaluated at J omega, and B will simply be the imaginary part evaluated at G evaluated at J omega. So if that were true, then I could say that Y steady state would equal A sine omega t plus B cosine omega t, which is close, but we have not yet shown that that's the same as our magnitude sine omega t plus phi, where m is equal to the absolute value of G sub P evaluated at J omega, and phi is equal to the angle of G sub P evaluated at J omega. So in order to get to this last, so we're here, and I think we've proven this, but to get to here, we've got to use the sine of alpha plus beta formula that we will look up on Purple Math next. So purplemath.org has a set of trigonometric identities that include this double angle formula. The sine of alpha plus beta is equal to sine of alpha cosine beta plus cosine alpha sine beta. And so my claim is that if we took that, so sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Triple check that I'm not miscopying that. Yep. And so my claim is that if we took the sine of omega t plus phi, we could write that as sine omega t cosine phi plus the cosine of omega t sine phi. And in that case, if we walk back up to here, then this is A, and this is B. So if that's true, then that tells me that the cosine of phi is equal to A. I guess I'm being just a little bit sloppy. I'm assuming that it's obvious that A squared plus B squared square root is equal to M. And this should probably actually be A over M. But it will not matter because I'm about to take their tangent. I guess I could show that. So if I did it that way, then if I said the tangent of phi was equal to sine phi over cosine phi, that would be b over m divided by a over m, and so the m's cancel, and we're left with b over a. Well, that turns out to be, if we fall back to here, that the tangent of phi is the imaginary part of gp evaluated at j omega divided by the real part of gp evaluated at j omega, which is exactly the definition of the angle function in Python that we'll see shortly. So that's good. Like I said, if I took this equation, how would I prove? Let me think about that for just a second. I'm making the claim that a squared plus b squared is equal to m squared, but I haven't really backed that up. Let me come back to that in just a second. So having thought about it, I realized that I had been a little bit sloppy in my derivation, which of course will be completely shocking to my students. So we have this y steady state is going to be a sine omega t plus b cosine omega t, and that's coming out of the partial fraction expansion after multiplying through by s squared plus omega squared and setting s equal to j omega. My claim is that we're going to write this as m sine omega t plus phi, where m will be the magnitude of gj omega, and phi will be the phase of gj omega. We did prove previously that a was the real part of g evaluated at j omega, and b is the imaginary part of gj omega. So the thing that I did wrong was fail to properly expand this as sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. So we could take m sine omega t plus phi and write that as m times the quantity sine omega t cosine phi plus cosine omega t sine phi. And so if that is supposed to be equal to a sine omega t plus b cosine omega t, then it will turn out that a is m cosine phi. And b will then be the stuff that multiplies cosine omega t, so that is m sine phi. So what we're left with is exactly what you would expect if we were talking about how to move between polar and rectangular forms for a complex number. So if I had some magnitude m at some angle phi, then this part would be m sine phi, which is also b, which is the imaginary part of g sub p j omega. And the real part is m cosine phi, which turns out to just be a. So if I've got a right triangle with side A and side B and hypotenuse m, then pretty obviously a squared plus b squared is equal to m squared. And I think it's pretty clear at that point that this claim is in fact justified. So a sine omega t plus b cosine omega t is equal to m sine omega t plus phi. And if we multiply that out in this way, we're saying that this is equal to this. A and b are defined like so, which does mean that the tan of phi is equal to b over a, which turns out to be the imag of g j omega divided by the real of g j omega, which is exactly the angle or phase definition for the polar form of a complex number. And similarly, if these things are true, then when I square and add them together, a squared plus b squared is equal to m squared times cosine squared plus sine squared, which is just saying that a squared plus b squared is equal to m squared. So in summary, just grab a new sheet of paper, quickly summarize what we're saying. If we have some plant transfer function that is y of s over u of s, and if u of t is equal to sine omega t, and if g sub p is stable, then we have shown that y, after all the transients die out, will be m sine omega t plus phi, and furthermore, that m is the magnitude of g sub p evaluated at j omega, and phi is the angle of g sub p evaluated at j omega. So that is the takeaway or the summary. Let's quickly look at this in Python to maybe bring this home with a numeric example. So if I have, I'm going to do some normal definition stuff. If I define a first order transfer function with a pole at 5 hertz or 10 pi radians, there is my transfer function using the Python control module. And if I want to specifically evaluate that at s is equal to 3j, the Python control module will let me simply plug that in, and I get this value. But I want you to see that that's exactly the same as taking 31.42 divided by simply substituting in 3.0j where s is, like so. I say exactly the same. There's a little bit of round off error because I'm only using so many digits of things, but that is accurate through a decent number of digits. So if I wanted to find this magnitude, there's an absolute value function in NumPy that will do that. And then I could, kind of doing this the hard way, take the arctan 2 of the imaginary part comma real part, and then actually define a radians 2 degrees. I could do that, so apparently that's a negative 5.455 degrees. But there's also an angle function built into NumPy, and so that would work, again, multiplying by radians 2 degrees. But angle can also take a comma 1, which means give me a degree result. If I don't have the comma 1 there, it's a radian result. So let's take a look at this same idea of we're talking about the steady state response, or the response after transients die out. So if I define some time vector and I create some u equal to sine omega t, and I define an s, I can find my magnitude and my phase. Note that now that I'm getting ready to use it like so, my phase is actually in radians. But my claim is that all I've had to do is evaluate g at j omega, find its magnitude and its phase, and I have the steady state response. And we're going to compare that to using the control.forced response, which is sort of like the numeric simulation way of doing a full partial fraction expansion. So this will get me y that includes both the transient and the steady state. Then I can plot these two on top of each other, and we'll zoom in on this in just a second. But the main thing I want you to see here is that I've got, first of all, an 85, so 15% reduction. The magnitude was 0.857. So this ought to be a peak of 0.857, so it's about 15-ish% smaller. And then it's got a little bit of phase lag compared to the input. Specifically, I actually didn't calculate. I think I calculated it above. Did I use the same S? So I'm going to assume that that's about a 5-degree lag. But if we wanted to know, we can find phi in degrees is equal to g sub 1 of s comma 1, and then we could output that. Oh, so that's 30 degrees. So apparently I'm choosing 6 pi here as opposed to previously I did just 3. Okay, so yes, phi is much different. So that's a 30-degree phase lag. It's a lag because it's negative. Yeah, and so the steady state agrees with the full response once the transients die out. And if we zoom in on that, you can see that there's a transient here that in this particular case lasts for a little over 1/10 of a second. So the green one has the proper initial condition and includes the full response that then dies out and becomes equivalent to the steady state response after about 0.15 or so seconds. Yeah, so if I want to find the steady state response to a sinusoidal input, I got to find just the magnitude and phase of the transfer function evaluated at, and we could talk about that for just a second just to make that clear. Evaluate the transfer function at S is equal to j omega, and I get some real and some imaginary component. I find the magnitude and phase of that and define a steady state Y is equal to m times sine omega t plus phi. And that works perfectly once the transient term dies out. Much simpler than doing a full partial fraction expansion. But this is also just paving the way for a Bode plot. So if I wanted to do this gj omega thing, I could do it at a vector of omegas multiplied by j, like so. That will give me a complex vector of the transfer function evaluated at every j omega in this vector. And then I can find the magnitude, or specifically the dB magnitude. So 20 times the log 10 is a decibel of the magnitude of GJ omega. And then I can find the phase in degrees with that comma 1 at every point. I'm also going to grab a few select points, specifically 1 Hertz, 10 Hertz, and 30 Hertz, to do a fixed sine analysis. But once I have the dB magnitude and the phase, we can represent that on a Bode plot, and we'll talk about how to sketch these in the next lecture, either flipped or live. But it's got a low frequency asymptote and a high frequency asymptote, and those intersect right about at P, where we defined P in this transfer function to be 5 Hertz. So these two lines, should intersect at about the 5 Hertz. So this is 1, 2, 3, 4, 5. I could sort of believe that. And below that, the magnitude is more or less equal to the input, and then it starts to roll off, and then the magnitude starts to be significantly attenuated, and the phase is initially roughly 0 degrees or in phase, and then eventually there's a 90-degree lag. So this Bode plot tells me the response to any fixed sine input within this frequency range, and I could easily expand the range that I'm generating it for. And it tells me what to expect both in terms of magnitude and phase relationship between the input and the output. How much is the input attenuated or potentially amplified, and how much is the phase lagging, or in some cases leading. And so this Bode plot is a super clear representation of how the system is going to respond to various fixed sine inputs, but also if I just had this experimentally, it tells me, oh, this is a first order system with a pole around 5 Hertz, and I can do that immediately just by knowing how to interpret a Bode plot, which will be again in the next lecture or two. And then at each of these 3 specific points, I've generated a fixed sine steady state response like so. And so here's the input, and there's just a little bit of lag at the 1 Hertz and a tiny, tiny amount of attenuation. I should have made it print M and phi each time through the for loop. And then at 10 Hertz, we see a little over 50% attenuation and a relatively significant phase, which would have been here, right? So we're at about -8 or 9 dB. I think -6 dB would be 50%, so that makes sense. And then our phase is at about -65, -70 degrees. So again, that makes sense. And then when we get to the 30 Hertz mark, we've got even more attenuation and now close to a 90-degree phase lag, which again, we're at -17 or 18 dB. I believe -20 dB is 1%. No, that's off. My math is off. Don't trust that. And we're about a -80 degrees phase. 40 dB is 1%. The issue there is take -20 and then divide by 20 and then take 10 to that power. So -20 dB is 10%. I could believe that. If this is 0.5, this would be about 0.25. So it's in the 10 to 15% range because it wasn't quite minus 20. And then my claim was that minus 40 is 1%. Yes, that I'm believing. And that has to do with a certain number of dB is equal to is equal to 20 times the log 10 of question mark. So you divide by 20 and then take 10 to that power to undo the log. Okay, that's not super important right now. So there you have it, a basic introduction to frequency response, how we find the steady state sinusoidal response based on that kind of analysis, and we'll pick up from here next time.